Today we're going to be talking about image classification with CNNs. So you might be wondering, who am I? I'm a new face. You haven't seen me before in this class. I'm Justin. I'm the fourth mystery instructor in this class. I think my picture's been on the website, but it's my first time here today. And a little about me. I did my PhD here at Stanford from 2012 to 2018, working with Feifei on deep learning, computer vision, pretty much all tasks in computer vision around that time. During my time here at Stanford, I was lucky enough to initiate CS231N with Andre and Feifei and others, and teach it, quite a few times, 2015, 16, 17, and 18, and 19. At Stanford. After that, I spent time at Facebook AI Research doing all kinds of deep learning, computer vision stuff there. I was a faculty member at University of Michigan. And there I taught basically the same class a couple more times. So I've taught this class a couple times, but it's been a while since I've been here. And most recently, I've been doing a startup called World Labs with Feifei. And that's just a little bit about me. Now, about where we are on this class. So we're kind of at an interesting point in the class right now, where the class is kind of divided up into these couple different segments. And we've basically finished the first segment. The first segment is basically around deep learning basics. And this is really cool because now all the stuff that you've seen in like 4 lectures is basically all the fundamentals of deep learning. You basically know this whole pipeline of what is the basic pieces that go into building a deep learning system. So I thought it's useful here at the beginning of this inflection point to just sort of step back and recap some of the major themes that we've seen in the first bit of the course. So the first is this idea of image classification with linear classifiers. And this was kind of meant as a toy problem to give you a sense of a kind of problem you might solve with deep learning. Where usually the first step in solving a deep learning problem is to define your problem in a way where it is, you take input some grid of numbers, some tensors, you produce as output some tensors, and you want to formalize this problem as some input-output of tensors. And we kind of do that in the image classification setting by saying that we want to classify images into a bunch of human understandable categories. The inputs are going to be these grids of pixel values, which are arranged in 3-dimensional tensors. The outputs are going to be scores, giving us the affinity or the degree to which, where we have 1 score per category. You define a set of categories in advance, and the network is supposed to predict high scores for categories that the image is likely to be, low scores for the categories that the image is likely to be not. And then we can set up a problem to, use a weight matrix, multiply that against the image pixels, and predict these scores. And we saw that there's a couple different viewpoints, a couple different ways that we can interpret these linear classifiers. And this basically sets up a functional form saying that we can predict scores for images if only we have a weight matrix W. So then the question is, how do we select a good weight matrix W? And for that, we go to loss functions, right? So loss functions are these things that tell us, given a particular value of a weight matrix, given a particular data set, how well does this weight matrix solve the problem on this data set? And in particular, we saw some examples of loss functions that are commonly used for classification problems, including the softmax loss and probably the SVM loss as well. And then now we've kind of gotten a little bit farther along in our problem. We've set up the problem of image classification. We have a model for solving that problem using linear classifiers. We have a way to tell if our solutions are good using a loss function. But now we actually need to search for a good solution in that space. And that's where optimization comes in. Right? So now you think of defining this optimization landscape where on the x-axis or on the horizontal plane are all the different possible settings of your weight matrix. And then the loss function is basically a height of this plane where a high loss function is bad because losing things is bad. So you want low loss. So the purpose of optimization is to somehow traverse this space, slide down this manifold and find a point at the bottom of very low loss. And now each point in this space corresponds to a weight matrix. So by sliding down that space, we're going to find a good weight matrix that solves our problem and gives us a good solution to our task. And in particular, we saw a couple different commonly used optimization algorithms that are used in deep learning pipelines. Stochastic gradient descent, usually with momentum, RMSprop, Atom. And one sort of interesting topical note is that right now, one of the biggest deep learning research conferences is ICLR, International Conference on Learning Representations. And just yesterday, ICLR 2025 gave their Test of Time award to the Atom paper. Because the paper that introduced this Atom optimizer was published at ICLR 10 years ago in 2015. So at a lot of academic conferences, they'll tend to give Test of Time awards to some of the most impactful papers from 10 years ago. And just yesterday, the Atom optimizer that you guys saw in this class got this very prestigious Test of Time award at ICLR 2025. So I thought that was pretty cool and a nice sort of way to connect what you've been learning to stuff that's happening right now in the machine learning community. Okay, so then now we basically, at this point, we've got our linear classifiers, we've got our loss functions, we can optimize them. Now we're almost good to go. But we ran into a problem, is that the linear classifiers that we started with are actually not very powerful. And we saw this from, we saw two different ways of attacking this deficiency in linear classifiers. One was from the visual viewpoint, where you can interpret a linear classifier by thinking of that learned weight matrix as an image, where you learn one image template for each of the categories that you're trying to classify against. And if you think about it that way, we realize that the weights of your linear classifier, each row of that weight matrix is one template. So the linear classifier basically needs to summarize all of its knowledge about each category into just one template. And that's kind of that's just not a very powerful classifier. So then this kind of shows up in these visualized templates of a learned linear classifier, where you can see that for categories like the car, this car kind of looks like a red blob. But cars don't have to be red, right? What if your car was blue or purple or green or something else? There's just no good way for a linear classifier to capture this notion of there might be different appearances for an object for each category. Or from the geometric viewpoint, if we imagine each point of our data set is some point in high dimensional space, then a linear classifier is basically going in and carving up that space with hyperplanes. So that's really good if all your categories actually do lie in linearly separable regions of your space, but there's no reason to expect that to be true in general. So these are both two big deficiencies that we ran into when looking at these linear classifiers as applied to image classification problems. And that led us to define this notion of neural networks, where we're going to generalize our linear classifiers to no longer just have one weight matrix, but instead stack two weight matrices on top of each other with a non-linearity in between them. And now this gives us a much more powerful mechanism for predicting scores from our inputs. Now basically the problem is still the same. We have our input pixels going through this computation, spitting out scores, but now rather than computing, but we just basically selected a different functional form for this score function. And this gave us and now, the algebra is pretty simple. You just need to go from f equals wx, you add an extra w2, add a little nonlinearity in between. So the algebra doesn't change very much. But in doing so, your classifiers get much, much more powerful than they were before. But now things get a little bit complicated again, because how does this play into optimization, right? We know that if we have a loss function, if we have a model, then we want to find values of those weight matrix that cause the loss to go down. And to do that, we need to compute gradients. We need to be able to compute gradients of the loss with respect to all the parameters of our model. And that's this notion of a computational graph. So these computational graphs are basically a data structure to organize the computation of a neural network, where each node in the graph is a little functional primitive, like a matrix multiply or a ReLU or something else like that. And then data flows forward in this graph from left to right, from our inputs and our weights on the left, flowing through all these intermediate nodes in the graph to spit out the loss function on the right. And then once we compute the loss, you traverse this graph backwards from right to left to compute gradients of that loss with respect to all the nodes of the graph inside the network. And this is now really cool because it basically means that we can write down these arbitrarily complicated neural networks, these arbitrarily complicated expressions for computing our outputs from our inputs. But we now have a nearly automated algorithm for computing whatever gradients we want through arbitrarily complex neural networks. And the way that we do that is this magic of backpropagation. And backpropagation is really cool. I think it's one of the algorithms that makes deep learning work because it takes this global problem of how do we compute the loss through this computational graph and converts it into a local problem. And now each of these nodes doesn't need to know anything about the larger context of what is the graph I'm living in, what is the problem I'm trying to solve. We just need to be able to define these little nodes inside of our computational graph that on the forward pass know how to compute outputs from their inputs, and then on the backwards pass can receive gradients coming upstream. It doesn't have to care where those gradients come from, what was causing those gradients to happen, and I just need to compute downstream gradients with respect to my inputs given my upstream gradients. And again, this is so powerful because now it gives us this mechanism where we can just define a bunch of different types of nodes that all just follow this local API of computing outputs, computing local gradients. And as long as we follow that API for all of the nodes, then we can start to stitch them together into these big complicated computational graphs that can do basically arbitrary computation. And the gradients just come for free when we turn the crank on the backpropagation algorithm. This slide, that you guys saw last time is basically backpropagation on scalar values, but we can generalize this to work on vector valued or matrix or tensor valued values as well. But the basic thing to remember is that your inputs are some tensors, your outputs are some tensors, and now your upstream gradient that you get is the gradient of the loss with respect to your outputs, and that always has the same shape as your outputs, right? Because the loss is a scalar. A gradient of a loss with respect to a tensor says, for each element in the tensor, if I were to wiggle that element a little bit, then how much does the loss wiggle, right? And because the loss is a scalar, we just need to wiggle each of those. We just need to imagine wiggling each element in our tensor independently, and that is the definition of our gradient. So then that's very easy to remember. Your upstream gradients always have the exact same shape as your outputs. Your downstream gradients, those are the gradients with respect to my inputs, those also have the same shape as my inputs, right? So then the backpropagation algorithm is basically just the chain rule where I need to somehow compute my downstream gradients as a function of my upstream gradients and whatever function I was trying to compute. And you'll get some practice on later assignments computing, writing down the gradient expressions for different kinds of operators in your neural networks. So basically, this gives us our recipe for solving pretty much any problem in deep learning, right? Like this was intended to be quite a bit more general than just image classification or just linear classifiers or just fully connected networks, right? Now, if you have any kind of problem that you want to solve, you just need to encode it as tensors, write down some computational graph that computes your output tensors from your input tensors, collect a data set of input-output tensors, write down a loss function for the kind of problem you want to solve, and then optimize that loss function using gradient descent, using backpropagation. And that's a really powerful recipe that basically powers all deep learning applications. Whether it's image classification, image generation, large language models, pretty much anything involving a neural network is trained using this formula or some slight variant on top of this formula. So that leads us to the second part of the class, which is perceiving and understanding the visual world. So here's where we want to get a little bit more specialized and start talking about, not the general framework of deep learning, but how does this apply to problems that we want to solve in computer vision, processing images, doing interesting stuff with images. And today we'll take a step towards that by talking about a bit more about convolutional networks. So convolutional networks actually are a pretty small lift on top of this framework that we've already defined. Right? So we've already talked about you have this sort of general paradigm of computational graphs, of little operators that can live inside of our computational graphs. So we have this beautiful framework, but we actually haven't filled in a lot of the specifics of that framework. We've actually only seen like 2 or 3 different kinds of nodes that can live inside of our computational graphs. We've seen fully connected layers, which is basically a matrix multiply. We've seen activation functions like our ReLU, and we've seen our loss functions themselves. And now to build up from what we've seen already into convolutional networks, basically all we need to do is add a couple new types of nodes that can fit into our computational graphs. And in particular, there's really only 2 operators that we need to talk about to build much more powerful networks, which will be the convolution layer that we'll spend most of today's lecture talking about, and then the pooling layer, which is another thing that we often use when processing images. So that's kind of the roadmap for today. I want to talk a little bit about convolutional networks in general. Then we'll talk about these 2 particular computational primitives that we can use to build convolutional networks in our computational graphs. Okay, so we've already talked about, so then here we want to step back a little bit and think about this problem of image classification again. So we've already talked about how image classification is this super core problem in computer vision, where we want to take an input image and then predict, from that input image, what is in this image as a set of category, predict one of k category labels, basically. And this image obviously is a cat, so we want to predict the cat classifier. We basically solved this problem in some sense already by building linear classifiers and by building fully connected multi-layer perceptron neural networks. But these networks are basically operating in pixel space. Their inputs, remember we said the first step to solving a deep learning problem is to formulate it in terms of input-output tensors. Well, in this case, our input tensors were the raw pixel values of our images. So when we write f of x equals wx, that x input, that's just the literal values of all of our pixels. And then we go from those raw pixel values to our class scores. But there's another way to do it, which was common back in the dark ages before neural networks came about and saved us from all this tedium, maybe back in the early 2000s, sort of up until maybe 2010, 2011-ish, was this idea of feature representations. So here the idea is you can actually choose what is going to be your input to your neural network. So you could have said, rather than feeding the raw pixel values of the network, of the image into our neural network, instead, we could define some other kind of function, which is going to extract features, convert those pixel values of our image into some other meaningful representation that we, as the intelligent human designers of this system, believe represent or capture some of the important facets of our input image. So then, if you're doing, image classification on top of a feature representation, your step one would be to define a feature representation that converts your raw image pixels into this higher level representation. And now that feature representation will now be the X that feeds into your linear classifier. And there was a ton of work in computer vision, really in the 2000s to the late 2010s, or to the early 2010s-ish, that used this idea of feature representations for all kinds of tasks. And I don't really think it's useful to go into super great detail on any of these particular feature representations because, spoiler alert, they got deprecated like 10 years ago. But it's useful to have a flavor for what they might have looked like. So one example of a kind of feature representation that people sometimes used is this notion of a color histogram. So here what we could say is divide the space. So maybe we think that somehow the distribution of colors in our image might be a useful thing for a classifier to look at or care about, right? Because maybe you're building a fruit detector, apple detector, and you want to know if it's ripe or not. Maybe a red apple from a green apple, knowing how much red or green is in the image might be something that we as humans think is useful for the network to know for making its classifications. So here, we could try to build a feature representation that captures that intuition. So here what we might do is take the space of all possible colors, discretize that space into some set of buckets. And now for every pixel in our image, we map that pixel to one of the discrete buckets in our color space. And then basically our feature representation becomes something like a count of how many pixels in the image fall into this color bucket. And now this is kind of an interesting representation because it destroys all the spatial structure of the image and it only talks about the color distributions. So now, if you had red in the corner versus red on the other side, those two images would look the same to this color histogram features, but they would look very different on the raw pixel perspective. So the color histogram is a kind of one basic kind of feature extractor or feature representation that you can build on images that basically looks only at color and does not look at spatial structure at all. Another category of feature representations that people used to look at is sort of dual to that, which are these histogram of oriented gradients. And I don't think it's useful to talk too much about exactly how these are computed, but the intuition of these is that they basically throw away the color information and they only look at the structure information. They basically want to look for every point in the image, what is the local direction of the edges in the image around that local region. So here you can see that this frog, the leaves of the frog, it kind of extracts diagonal type of features because it corresponds to these diagonal structures over here. Or around the frog's eyes, you can see, it sort of captured those circular structures. So again, it's not super useful to see how this is computed, but it's useful to know that these are the kinds of features that people would design for images maybe a decade or decade and a half ago. And people combined these in all kinds of complicated ways. So people would often ask, you might wonder, what's the best feature representation? The usual answer was just stack them all together. So a pretty common approach would be to have a bunch of different feature representations, extract them all from your image, and then concatenate them all into one big feature vector. And that's kind of becomes your feature representation for your image. And now you could imagine once we have this feature representation, we can basically stick whatever kind of classifier we want on top of it. And it's interesting to then take a step back and contrast that picture, that viewpoint of that whole system. So system A is thinking about feature extractor plus learned network or learned linear classifier on top of your features. And then system B is end-to-end neural networks. And they actually don't look that different if you take a step back and think about it in the right way. Both of these systems are ultimately inputting the raw pixels of the image and outputting some scores or predictions about the image. The difference is that the difference is which part of the system is designed by humans versus which part is learned via gradient descent. In the feature extraction plus linear classifier paradigm, the feature extraction portion of the system is designed. That could be a bunch of really hairy C code or hairy MATLAB code. And you don't want to think about the details of what's going on inside of that. And then just the part that you're learning via gradient descent, the part that you're learning from your training data, is just that classifier on top of the feature extractor. Whereas the neural network approach is basically saying gradient descent is probably a better programmer than you, and lots of data probably knows more about your problem than you do. So then the intuition of these neural network classifiers is there's still ultimately going to be a system that inputs the raw pixel values and spits out your classification scores at the end. But the difference is that all parts of that system, from the raw pixels all the way to the final classification scores, will be tuned via gradient descent and will be learned from your training data set. So the intuition is that, there might be, in this feature extraction paradigm, there might be some bottlenecks. You as a human might get something wrong. You might have wrong intuition about what parts of the problem are important, what things are not important. Or it might be really hard for you to write down the perfect feature extractor that solves your problem. And this end-to-end learning approach of ConvNets and really of deep learning more generally is just saying that data and compute can likely solve that problem better than you as a human designer can. And this paradigm has basically won over the past decade and a half for lots and lots of problems repeatedly. Okay, so that kind of gives an intuition of, so then the question is like, for the particular problem of images, how should we design these end-to-end systems, right? Like, it's not going to be a fully connected network all the way. That would be a little bit silly. We do need to still put a little bit of design into the system. Right? But the difference about designing a neural network versus designing a feature extractor is that in designing a neural network, you're not designing a particular function of a feature extractor. You're kind of defining a whole category of functions, where the category of functions is defined by the structure of your computational graph, by the sequence of operators that get run. But there's some flexibility in that system because you're leaving the weights of the system free to be learned from data. But the role of the human designer still matters. You still need to decide what is that architecture of your network. What is that sequence of operators that get stitched into a computational graph? What are the sizes of all the matrices involved at every stage of processing? So there still is a lot of role for the human to design parts of the problem in this deep learning era. But what you're designing is a little bit different. So this is basically where we start to see the deficiencies in the tools that we have so far for solving this problem, right? Because we see that we've seen linear layers, we've seen fully connected networks, and the kind of only neural network architecture that we've seen is to flatten our pixels of our image into a big vector, do matrix multiply, do ReLU, do more matrix multiply, do more ReLU, and that's about it. That's all we know how to do at this point. And one big problem with that is that it destroys the spatial structure of the images. There's this big problem, right? Like, it's sort of like images are actually not one-dimensional objects. Images are two-dimensional. They have two-dimensional structure. That two-dimensional structure matters for the content of those images. And when you build a linear classifier on raw pixels by stretching it out into a big vector, you're basically ignoring that important factor of your input data in the design of your neural network architecture. So when we think about designing neural network architectures for images in particular, we want to think, what are other designs for our network? What are other computational primitives we can slot into our computational graphs that better respect that two-dimensional structure of images? And that leads us to convolutional networks, right? So convolutional networks are basically a category of neural network architectures that are built of linear layers, non-linearities, convolution layers, pooling layers, sometimes a couple others, that stitch together into these neural network architectures that input raw pixel values and then output some kind of prediction or scores for our images. And the general structure of these is that usually they'll have some prefix, some body of the network, which is some interleaved sequence of convolution layers, pooling layers, and nonlinearities that can be thought of as extracting some useful feature representation for the image. And then on top of that, there'll usually be some kind of fully connected layers, sometimes as few as one, but sometimes more than one, which you can think of as a multi-layer perceptron fully connected network classifier that lives on top of and ingests the features from the convolutional portion of the network. But crucially, this whole system is tuned end to end via gradient descent by minimizing the loss on your training data set. And these networks actually have quite a bit of long history. So this image, this particular ConvNet architecture that we've drawn on the screen, actually comes from a paper back in 1998 with Yann LeCun, Leon Bateau, and others, who were at the time building these convolutional neural networks all the way back in 1998 to perform the task of digit classification. And it actually worked pretty well, but it was really expensive. They didn't have GPUs, they didn't have TPUs, they didn't have the kind of compute resources that we did today. But the underlying algorithm, the underlying network architecture, basically looks pretty similar in 1998 to what things were to the kinds of architectures that people were using well into the 2010s. And then zooming forward from 1998 up until 2012, that's when the AlexNet architecture came out. And this was kind of a big boom, like giant explosion of deep learning, especially in computer vision. And I think we talked about this in some earlier lectures. But the AlexNet architecture, again, like doesn't look that different from this Yann LeCun LeNet architecture from 1998. It's a bunch of convolutional layers, fully connected layers. It's bigger. There's more layers. The layers have more units in them. But it's still trained end to end with backpropagation to minimize some fairly simple loss functions. But here, like AlexNet was when really things started to take off. And at this time, they were able to train on GPUs. GPUs were available. There was more data available because of internet, because of ImageNet. So AlexNet is when things really started to take off. So then the era from, I think, about 2012 to around 2020-ish was an era where convolutional networks were basically dominating almost every problem in computer vision. They were solved, like basically any kind of a problem that you wanted to do with an image. In that era, it was almost certainly going to be a ComNet that had the best performance on that problem. So this included tasks like detection on the left, which is the task of not just classifying an image, but drawing a box around all the objects in the image and putting a category label on the box. Segmentation is the task of assigning labels not at the box level or the image level, but instead assigning labels at the pixel level. So now we want to assign a category label to every pixel independently in our image. And we'll talk more about architectures for these problems in future lectures, but these can be solved very effectively using convolutional networks. People used ComNets for other kinds of problems involving language as well. So the task of image captioning, where we want to predict a natural language caption from an image. Some of the first widely successful approaches to this problem also were built on convolutional networks. And then even for some more recent tasks of generative modeling, right? So captioning is basically the problem of an image to text, where we input an image and then want to output a natural language sentence describing the image. We can also think about the inverse problem of text-to-image generation, where we want to input a natural language description of something that we're imagining in our head and have the system generate a new image from scratch that, hopefully matches our input description. And some of the first really widely successful versions of this problem also were built on convolutional networks. So this particular figure is from the Stable Diffusion paper that came out back in 2021. And this technology has gotten a lot better in the last couple of years, and we'll talk more about that in some later lectures. But it's useful to point out that this basically, the first versions of this that started to work really well were also built on convolutional networks. So basically, convolutional networks were so important for this history of computer vision that the initial version of this class that we started way back in 2015 was actually called Convolutional Neural Networks for Visual Recognition. Because at the time, convolutional networks was basically synonymous with computer vision. And computer vision was basically the biggest field that was benefiting from deep learning at that time. So in setting out to teach a class about deep learning, it actually made a lot of sense to focus entirely on the problem of convolutional networks for image problems. And that's basically the inception of this class 10 years ago. But the field has actually evolved a lot since then, right? Convolutional networks have actually gotten replaced. Visual recognition, there's a lot of other interesting problems that we can solve now. So you'll notice that the name of the class changed at some point along the way, and to no longer focus so specifically on convolutional networks. And the reason for that is that, I said this was the era from 2012 to 2020. You might be wondering what happened in 2020 other than COVID that could have displaced convolutional networks. It wasn't COVID, it was transformers, right? So transformers are this alternate neural network architecture that we'll talk about in a couple more lectures. But basically they started off in natural language processing for processing documents, for processing text strings. And the transformer architecture got first published in 2017. And for a couple years after that, it mainly stayed in the regime of processing text. But there was a really important paper in 2021 that basically applied nearly the exact same transformer architecture that had been getting used to process text, to process strings, and instead used it to process images in nearly the exact same way. And since then, people have found that for a lot of the previous problems that we just talked about that were previously solved using convolutional networks, you could replace the CNN with a transformer keep everything else the same, and you tend to get better performance on these problems. They scale up to more data, they scale up to more compute, and we can get more data, we can get more compute, so these are much more commonly used for more and more computer vision problems these days. And we'll talk much more about transformers in lecture 8, but I thought it would be weird to be pitching convnets super hard when actually they don't get used quite as much nowadays as they did maybe 5 years ago. But I still think it's really useful to talk about convolutional networks. One, because there is a lot of historical significance. Two, these algorithms still do get used quite a lot in practice. Three, it helps you build intuitions about what's important for images. And four, they're actually not completely dead, right? Like a lot of times we're actually building hybrid systems. Sometimes we use convolutions, sometimes we use transformers, sometimes we mix them together in various ways. So it's actually super useful to still know about this stuff. So then basically, the rest of today, we're going to talk more about convolutional networks. We said that a convolutional network is just a computational graph for processing images that's built from a couple different primitives. We've already met the fully connected layer and the activation function, so we basically need to walk through these two more layers of the convolution layer and the pooling layer. Quick recap of the fully connected layer. This is what we've already talked about in the context of linear classifiers. So with our fully connected layer, like we said, basically what we do is we take our pixels of our image. Our image is this three-dimensional tensor, 32 by 32 by 3. 32 by 32 are these two spatial dimensions. 3 are 3 channel dimensions for your RGB colors. So we take that 32 by 32 by 3 vector, you stretch it out into a long vector of 3072, because that's, if you multiply those in your head, that's the number you get. And then you have basically this vector of 3072 numbers. We have a weight matrix that's 3072 by 10 in this case, because 10 is the number of output classes that we want. You do a matrix vector multiply between those two, you end up with a vector of 10 numbers, giving us our class score. And in particular, it's interesting, in trying to generalize this from fully connected layers to convolutional layers, it's useful to think a little bit more about the structure of what this fully connected layer is doing, right? That fully connected layer, the output vector contains 10 elements. Each one of those elements is a single number. Each one of those numbers is predicted by computing an inner product between one of the rows of your weight matrix and the entire input vector, right? But each entry you should basically think of as a dot product. And a dot product you should basically think about as a template match, right? Because the dot product between two vectors is high when the two vectors point the same way, and it's 0 when the two vectors are orthogonal. So anything built on dot products is basically a kind of template matching. So the way that you should think about these fully connected layers is that we have a set of templates. Each of the templates has the same size as our input, and then the output is the template matching score between each one of our templates and the entire input. So then, once we think about it that way, there's actually a nice way we can generalize this from fully connected layers into convolutional layers. And that's by saying, we're still going to have this notion of template matching. We're still going to have this notion of learning a bank of filters. But what we're going to change is that those filters those templates are no longer going to have the same shape as the input. Instead, now our filters will only look at a small subset of the input. So more concretely, rather than stretching out our image into a big vector of 3072 numbers, instead we're going to maintain the 3D spatial structure of our image. It's going to now be a three-dimensional tensor of 3 channels, sometimes called depth or channels dimension, 32 width, 32 height. And now one of our filters is going to be a tiny little sub-image, a tiny low-resolution image, in this case a 5 by 5 pixel image. And importantly, that small filter needs to have 3 channels. The channels are always going to span the same as the number of channels in the input, but the spatial size will be smaller. And now what we're going to do is we're going to compute dot products. We think about that small filter as a little chunk of image template, and we're going to slide it everywhere across the image and say, for every point in the image, how much does that subpart of the image match this template that we're learning in our convolutional filter? So we'll plop that convolutional filter down at some chunk of the image. That 5 by 5 by 3 filter will line up with some 5 by 5 by 3 chunk of the image at that spatial location. We'll compute an inner product between those two, and that will give us one single scalar number telling us how much does that chunk of the image align with our template. And now we'll repeat that process and slide that template everywhere in our image. And every place that we plop down that template, it'll give us, we'll again compute this template matching score that says how much does that piece of the image align with that one template. And as we slide that filter everywhere on the input image, we're going to collect all of those scores, all of those template matching scores into a plane, right? And that plane will now be a two-dimensional plane that says, basically, for every point in the plane now corresponds to how much did that corresponding piece of the input image align with our filter. But of course, this is deep learning. We want a lot of compute. And how do we get more compute? We have more filters. So now we'll add a second filter, and we'll say, we'll repeat the whole process again with another filter. So we had a 5 by 5 by 3 filter that we colored in blue. Now let's imagine a second filter that's now colored in green. Our second filter will still be 5 by 5 by 3, and we'll repeat the exact same procedure of sliding that green filter everywhere on the image, compute template matching scores between the green filter and little sub-pieces of the image, and then collect all of those scores in a second plane, telling us, for every point in the image, how much did it respond to the green filter. And now we can basically iterate this and add as many filters as we want. So then, in this case, we are drawing 6 filters. Each of them is going to be 3 by 5 by 5, or 3 by 5 by 5. So then we can actually collect all of those filters into a single 4-dimensional tensor, right? So that 4-dimensional tensor now has 6 is a leading dimension because we have 6 filters. And then that 3 by 5 by 5 is that image template, is that template that we're learning. And now the convolution layer basically takes as input our 3-dimensional image and our 4-dimensional bank of filters, slides all the filters everywhere on the image, and gives us these response planes. So then once we collect all those response planes and stack them up in a 3rd dimension, then our output has size 6 by 28 by 28, where 28 by 28 should be interpreted as spatial dimensions, and that 6 is a channel dimension. And of course, we'll also, just as we do with linear layers, we'll often add a learnable bias vector as well to our convolutional layers. So that then in that sense, it's sort of, in a linear layer, a bias is one scalar per row in the linear layer. Correspondingly, in a convolutional layer, we'll have typically one scalar bias value for every filter in our convolutional, for every one of our convolutional filters. So that means that we'll have a 6-dimensional bias vector in this setting. Yeah, the question was clarifying 3 as the RGB channels. Yeah, that's correct. The question is, how do you get the filters? That's through the miracle of gradient descent and backpropagation, right? So the idea is that we're defining this operator. This operator is going to have an input image and a set of filters, but no human is going to define what those filters are going to be. Instead, we're going to initialize those filters randomly, and then they'll be learned via gradient descent on whatever problem you're trying to solve. So that's actually a really important thing to keep in mind, and that gives these layers their power, is that we're defining this fairly computationally expensive layer, but we're expecting that it'll be filled in with the data and compute from our training. Question is, how do you set the 5? That's a hyperparameter. So, we talked about hyperparameters and cross-validation a couple lectures ago. So these would be architectural hyperparameters that you would typically set via cross-validation in some way. Yeah, good question. Does it make sense to have different sizes of filters? So as we'll see in the CNN architectures next lecture, actually, I think you're going to talk about inception. Sometimes you actually do have that, but that typically happens at there's kind of a nice API design problem when you're designing what is a primitive in your computational graph versus what is going to be an emergent structure built out of primitives. So in this case, we usually define a single convolutional layer as having a fixed filter size because that makes it easier to compute and write efficient GPU kernels. But if you can effectively have multiply sized filters by stitching together a computational graph that combines convolution layers with different filter sizes in a larger network structure. So it's sort of yes and no is the answer to your question. The question is, what are we learning? And this is very important to distinguish between a parameter versus a hyperparameter. So a hyperparameter is something that we set before we start training the network. So in this case, one of the hyperparameters would be the number of filters and the size of those filters, because those set the shapes of our tensor, right? So then a parameter is a value that we're going to set and optimize over the course of gradient descent. So in this case, the number of filters, the number of output channels, the size of those filters, those will be hyperparameters. We set those once before we start training. At the beginning of training, we'll randomly initialize the filters, and then the value, and that will give us a fixed shape, fixed size tensor. And then the values inside of that tensor will float around and change over the course of optimization. So then those are parameters because they get set via gradient descent. Yes, the question is, what gradient are we computing? Whenever you do backpropagation, you're always computing gradient of the loss with respect to things inside the network. So in this case, we'll be computing gradient of the loss with respect to the individual scalar, with respect to our convolutional filter weights. So that's basically saying, what is a gradient? That's saying for every individual scalar inside of every one of our filters, if we wiggle that scalar a little bit, then how much is the loss going to change? So then the gradient of the loss with respect, we're always computing gradient of the loss with respect to our convolutional filters. The question is basically like, what do we do with the bias? So basically the bias would be added to each of our inner products. Right? So then we'll always compute like inner product of one of our filters against a chunk of the image and then add the corresponding scalar from the bias. The bias is a vector, but the number of entries in the vector is equal to the number of filters. So then each entry in the bias gets basically broadcast across the entire spatial dimension in the output, but each bias only gets used for one bias gets used for one filter. So conceptually, you basically, one filter, you slide everywhere, that gives us a two-dimensional plane of activations, right? And then if you have a second filter, you get a second plane of activations. Those are independent operators, right? Like step one, slide first filter everywhere. Step two, slide the second filter everywhere. Every filter gives rise to a plane that we call an activation map. And then we stack all of those up. And that's the operation of the convolution layer. Question is, basically after every gradient descent, every time we do gradient descent, it's going to change the filters, right? So whenever you imagine training a neural network, it's always this loop of like, while true, get a batch of data, send your data through the network, forward pass, compute loss, backward pass, compute gradient with respect to loss, and now make a gradient step using your optimizer. So then it's always going to be data, forward, loss, backward, step. And then every time you do a step, it's going to make a change to the filters. All right, so I swung the other way. I said more questions. I got too many questions, but that's good. We'll kind of equalize in here. Okay, so then we talked about the convolution layer. It's actually pretty common in the convolution layer to work on it in a batched mode. So rather than working on one input image, we'll actually work on a batch of input images. So this is kind of nice because it makes everything four-dimensional. Now we have a four-dimensional tensor of inputs, which is a set of input images. We have a four-dimensional tensor of filters, which is a set of filters, each of which is a three-dimensional chunk of an image. And then the output is a four-dimensional tensor, which is a set of outputs. Each output, one output per image. Each image's output is a three-dimensional tensor giving a stack of feature planes. You have to start to think in lots of dimensions when you start to build neural networks, and that's actually kind of fun. So then here's kind of the general formulation of a convolution layer, is that in general, you're going to take as input a four-dimensional tensor of n by cn by h by w, which is a set of n images. Each of those n images has cin channels. For the case of an RGB image, that'll be 3, but we might in general have more than 3 channels. This could be arbitrary. And then h and w is the spatial size of our input images. Our convolutional filters will be a four-dimensional tensor of shape Cout by Cin by Kw by Kh. Cout is the number of filters, the number of output channels. Cin is, and then the rest of that are three-dimensional filters. So it's a set of three-dimensional filters. Each three-dimensional filter has shape Cin by Kw by Kh. That's the kernel width and kernel height. And then we have Cout such filters that get collected into a four-dimensional tensor. And then as output, we're going to produce a four-dimensional tensor, again, where the shape is n for the number of images, one output per image. Cout, each of those outputs is going to consist of Cout feature planes, one per filter. And then each of those planes is going to be h prime by w prime. And this is kind of the general formulation of a conv layer. And then a convolutional network is just a computational graph that includes a bunch of conv layers. So in practice, we'll tend to stack up a bunch of convolutional operators, one after another. And in stacking a bunch of convolutional operators, that will be a convolutional network. So this is kind of a simple convnet. You start with an image that's 3 by 32 by 32. Then we have a conv layer that has 6 filters. Each filter is 5 by 5 by 3. Then after we do the first convolution, that gives us a new three-dimensional set of activations for that one image, where we have 6 channels that matches the 6 filters, 28 by 28 because the spatial size changed a little bit through the convolution. Then we have another convolution that now has 10 filters, each of which is 5 by 5 by 6. So the 10 is going to give us the output dimensions in the next layer of the convolution. And this 6 is going to be the number of channels that needs to match up the channel dimension here of the input to the convolution. So you can kind of see, like, you can just stack up a bunch of these convolution layers and perform a lot of computation. But there's actually a problem in exactly this network architecture design. And can anybody spot it? Sizing, that's a problem, not the one I had in mind. Convolutions are local. That's another good problem, not the one I had in mind. Actually, those two we'll be able to fix pretty easily in a couple slides, but I had a different problem in mind. A lot of memory, that is a problem, but not one we can fix. You just gotta buy a bigger GPU. Number of filters increases. I don't think that's a problem necessarily. That's okay. Everything's linear. Yes, that is a problem, right? So we said that a convolution was dot products. Dot product is a linear operator. Composition of two linear operators is still a linear operator. So that means that if we have two convolution layers stacked directly on top of each other, they actually have the same representational power as a single convolution layer because of the linearity of the operator. There's actually a very simple fix to that. Add an activation function. Exactly. So it's actually the same bug that we saw in multi-layer neural networks and the same fix. We need to add a nonlinear activation function in between our convolutional layers. If we want it, this introduces nonlinearity to the problem, nonlinearity to the network architecture, and increases the representational power of the network that we're learning. So, in general, convnets are going to be some stack of convolution layers, nonlinearities, and other kinds of layers in our computational graph. There was a question earlier about what do the convolutional filters learn. This is basically, we can view this by analogy with what we already did in linear classifiers. So in linear classifiers, we have this intuition where each row could be visualized, each row of the learned weight matrix could be thought of as a template that has the same shape as the whole input image. Now with a convolutional filter, you can think of it the same way. But now each filter, rather than extending over the entire spatial size of the input image, is going to be just a small sub-piece, a sub-chunk of an image. So we can actually visualize the first layer convolution filters of a trained neural network. So these are the first layer convolution filters that are learned by an AlexNet architecture that was trained for image classification on ImageNet. And here, each of these are basically little chunks of RGB images. These are the little templates that get slid around the input image in the first layer of the AlexNet architecture. The fact that this was AlexNet, the fact that this was trained on ImageNet, the fact that this was classification, it turns out just about all convolutional networks end up learning filters that look something like this on almost all problems and almost all data sets and tasks, as long as they're sort of reasonable tasks. And the thing we see is that we often learn two kinds of filters in here. One tends to be looking for colors, especially opposing colors. So you'll see like this one is looking for a contrast between green and red. We also see colored blobs like pink and green blobs. And the other category of filter we tend to see are looking for somehow the spatial structure of the images. So like this one is looking for a vertical edge, a horizontal edge. This one is looking for a vertical edge. Some of these are looking for diagonal edges. So they tend to look for colors and edges, and like in these little local neighborhoods of our input images. So we can play this trick on the first layer of the convolutional filter and just visualize them directly as images. It gets a little bit trickier to visualize the higher layers in the network. And I'm not going to explain this figure. I'm just going to present it without too much explanation. But higher layers of the network tend to learn larger spatial structures of our input image. Here the visualization is like each row represents a filter in a learned network, and each column represents some piece of an input image that filter was responding strongly to. So the visualization here is a bit different than the previous slide. So these are all basically chunks of input images that a filter was responding to. And here you can see that this sixth layer convolution, one of these filters feels like it's responding maybe to eyes. This one looks like maybe it's responding to pieces of text. This one looks like maybe it's responding to wheels or circles or top halves of circles, something like that. And again, like this all sort of gets driven via gradient descent, via training on your large-scale data sets via gradient descent. Nobody's sort of sitting down and designing these filters by hand. And like I said, visualizing these higher layer filters is a bit tricky and more involved. Question was, if you look at all the responses to the filters, can you reconstruct the original image? Actually, it turns out you can do that. And the way that you do that is also gradient descent. Gradient descent is really powerful. And that's something that we'll talk about, I think, in a couple more lectures on some mechanisms that do that. Oh, that's a good question. How do the filters get differentiated? That actually comes down to the random initialization, right? So then it's really important that the way you initialize your filters is random, and crucially that you have a different initialization for each filter when you start training your network, because that's going to break the symmetry between the filters, right? Because if all the filters are exactly the same, the loss is the same, then that gradient is going to broadcast back and be the same on all the filters. So if you initialize them the same, they will stay the same. But if you initialize them to be different, then you'll break the symmetry and they can learn different features. Yeah, basically the human designer of the network needs to write down what is the sequence of operators and the sequence of channels. And that's the question of neural network architecture design that we'll talk a little bit more about in the next lecture. Good question is how do we, why is it that the deeper layers visualize larger structures? That actually has a bit to do with the receptive fields that we have a slide on in a little bit. So maybe we'll get there, and I think some of these questions will get answered. So one thing that already came up is how do we look at the spatial dimensions of these convolutions? So I wanted to take a closer look at exactly how we compute the spatial dimensions of our convolutions. Right? So in this case, here we've taken this picture of a convolution, we're rotating it 90 degrees and dropping the channel dimension. So now the channel dimension is going into the board, and then we have our 7x7 spatial dimensions. So here we're looking at an input that's 7x7 in spatial size, and we have a 3x3 conv kernel. And then the question is, how big is our output going to be here? Well, 1, 2, 3, 4, 5. Right? So our output is going to be 5x5 because we can slide that filter and plop it down in 5 different spaces. And then we can generalize it, right? If our input has length w, our conv filter has length k, then our output is going to be w minus k plus 1. And you can sit down and convince yourself that that's the right formula. But there's kind of a problem that actually a couple people already pointed out, is that your feature maps are going to shrink in spatial size as you go through this convolution. That's kind of annoying. It's actually, you could actually work with that, and there are some neural network architectures that deal with that, but sometimes we're lazy and we just want to keep the same size for everything because that's just basically simpler for human designers to think about. And one trick that we do there is something called padding. So here it's common to add additional data, like virtual data around the input of around your true input data, that you're gonna basically add extra zeros, around before you compute the convolution operator. And now in this basically lets us solve this shrinking feature map problem. Because now if we have, add padding of p, in this case we have padding p equals 1, so we're adding 1 pixel of zeros all around everywhere, then we basically add 2p to our output size. So in particular, if you have a 3x3 conv and you add padding of 1, then your feature map is going to stay the same size. And that's convenient. Now, if you've taken signal processing, there actually are some problems here, right? This can lead to weirdness from a signal processing perspective, but we'll ignore that and we'll just look at the sizes and shapes of the tensors because that's a little bit easier to comprehend. But be aware, why are we putting zeros? Is that going to cause problems? Yes, it is going to cause problems on the borders, but it seems to be okay in a lot of cases. Okay, yeah, so then, like I said, a pretty common setting is to set p is to have actually k be an odd number, and then have p be k minus 1 over 2, because that's going to mean that your spatial size after convolution is the same as the spatial size before the convolution. Okay, then the next interesting thing to think about is this notion of receptive fields. Someone was asking a little bit over here, why do the deeper layers learn larger structures? That's actually sort of inherent in the way that convolutions are built. Right? So in thinking about a single convolution, each output is looking at this local region of an input, right? So by design, the output of one convolution at the first layer can only be looking at a piece of the image, which is the same size as the convolutional kernel that you're learning. But if we build a convnet that's stacking multiple convolutions on top of each other, then these receptive fields get magnified through the network. So then, in this case, we're looking at a network with 3 convolution layers. And we see that in the final layer of activations, each entry here depends on a local region in the layer before it. But each one of those entries depends in turn on a local region in the layer before it, which depends in turn on a local region in the layer before it. So when you have these convolutions, even though each individual convolution is looking at a local neighborhood in the layer before it, as you stack up convolutions in a bunch of layers, then the effective size of the original input that each of those convolutions is looking at grows over the course of the network. And in particular, this we call the effective receptive field. So the effective receptive field of a convolution is basically how many pixels in the original image had the opportunity to influence one activation of the network, later on downstream. And you'll notice that the convolution actually, this effective receptive field basically grows linearly with the number of convolution layers. And there's a potential problem here, is because ultimately, when we make classification decisions at the end of our network, we would like our classification decisions to basically aggregate global information across the entire image. But you need a lot of conv layers to do it. So a trick there is basically to add some kind of way to increase effective receptive fields more quickly. One way that we can do this in convolution is by introducing something called a stride. So here what we're saying is that rather than placing the filter everywhere in the image, we're going to skip some. So we're going to, instead of moving the receptive field with 1, we're going to stride it by 2 instead. So now in this case, we go back to our 7x7 input, 3x3 conv, do a stride 2. Now what's the output size? 1, 2, 3. 3x3. And then in general, if we have our input W, filter size K, padding of P, stride S, then we get this kind of ugly formula for the size of the output. W minus K, the bigger kernels shrink the input, plus 2P, padding adds back some of the missing size, divided by the stride, divides the input shape, and then plus 1 because of some fence post math. Okay, so then the strided convolutions are interesting because if you go back to this picture, now when we do a strided convolution, it's effectively downsampling the image inside the neural network. So then when we have a strided convolution, then each conv layer is effectively like dividing the shape of the feature map, usually by 2. And then when we stack these, that means that now you can get exponential growth in the effective receptive field. So if you stack a bunch of conv layers, and each of those conv layers is actually downsampling by a factor of 2, then if you run through a similar exercise, you'll see that the effective receptive field is now growing exponentially in the depth of the network. So that means that with relatively few layers, we can build up a very large effective receptive field that looks at the entire input image. Okay, so here let's work through just one example to make sure that we all are on the same page about convolution. So here, let's think about an input volume, 3 by 32 by 32. Let's think about a convolution layer with 10 filters. Each of those filters is 5 by 5, with stride 1, pad 2. What's the size of the output? I color-coded it because there's a lot of numbers here to keep track of. Right, so here, it's 10 by 32 by 32. This 32 is actually a different 32 than this 32, so that's why they're different colors of blue. Right, but this 10 is the number of output channels. Output channels has to match the number of filters. And the spatial size is computed using that formula that we just saw. So then the input spatial size comes down here, plus the padding comes down here. Padding adds the spatial size. 5 is the convolutional kernel. That divides the spatial size. Stride of 1, so that's trivial, and then add 1. And this just so happens to come out to 32. So in this case, this follows the same pattern that we talked about a couple slides ago, where it's an odd-shaped convolutional kernel, in this case 5. The padding is 2. So if the kernel size is 2k plus 1, then padding of k means we maintain the same spatial size. Number of learnable parameters here. Maybe I'll just go through these because we have a couple more slides to get through. So here, in this case, number of learnable parameters is 760 because we have each filter is basically 3 by 5 by 5, and we have 1 for the bias. So we have 76 learnable parameters per filter. We have 10 filters, so it's 760 learnable parameters here. We can also compute the number of multiply add operations. How much compute does this convolution operator take? So here, it's a lot. Well, is it a lot? I don't know. I don't have a lot of, you may or may not have a lot of intuition for what is a lot of computation. But in this case, the way that I think about computing how many flops, how much compute does a convolution operator take, we think about what the output volume size is 10 by 32 by 32. And we know that each entry in that output volume was computed via a dot product. A dot product in particular between one of our filters and a chunk of our input. So in this case, we know the total flops because we know the number of outputs is 10 by 32 by 32, which is about 10,000. And then each of those outputs is computed via a dot product of a 3 by 5 by 5 filter and a 3 by 5 by 5 chunk of the image. So that's 75 elements. So multiplying those together, it means it takes about 768,000 floating point multiply add operations. Okay, so then here's the kind of one slide summary of convolution. I'm not going to walk through this. This is more for you to look at later, but this just summarizes all the hyperparameters and the formulas associated with convolution layers. If you look in PyTorch is the deep learning framework that a lot of people use. There you'll see this convolution layer has all these hyperparameters that we talked about. There's a couple other interesting hyperparameters that we didn't talk about called groups and dilation. Dilation isn't really used so much anymore. Groups still get used sometimes, but maybe we'll talk about those in a later lecture. You can have other kinds of convolutions too. So we talked about 2D convolution. We can also do 1D convolution, where rather than having a 2-dimensional signal that we slide a filter over, we now have a 1-dimensional signal that we slide a filter over with 1 degree of freedom. or a three-dimensional convolution, where we have a three-dimensional signal, a three-dimensional filter, and now you can slide that filter everywhere in 3D space to convolve with the input signal. So this idea of a convolution really extends beyond just two-dimensional images. Okay, so that's basically all about convolution. And the last one is pooling. Thankfully, pooling is pretty simple. So pooling layers are basically another way to downsample inside of your neural network. So we saw that strided convolution is one way that we can downsample inside of a neural network. And downsampling is useful because it lets us build up receptive fields more quickly as we go through the depth of the network. But convolution actually still costs quite a lot of computation. So convolution, is where most of the flops, most of the compute happens in a convolutional network. And pooling layers are basically a way to downsample that's very, very cheap, that doesn't cost a lot of compute. And the idea in a pooling layer is given our three-dimensional tensor, where in this case 64 by 112 by 112, you should think about that as like a three-dimensional volume of features, where the spatial size is 112 by 112, and we have 64 planes, 64 channels of activation. So now and each one of those planes is a 112 by 112 image. But then what we're going to do is take each one of those individual feature planes, pull it out from our input tensor, and downsample them independently, and then restack them to compute the output. So then this input 64 by 224 by 224, we're going to pull out each of those 224 by 224 planes, independently downsample it, and then restack them to give the same number of channels, but change in the spatial size. What is the method we use for downsampling? Great question. That's actually a hyperparameter. There's a couple different mechanisms of downsampling that we use. One of the most common ones to use is called max pooling. So in max pooling, what we're going to do is take our single depth slice, divide it up into non-overlapping regions. In this case, these are and we often use the same terminology to talk about these as we do with convolution. So this we could say it's a kernel size 2 by 2 with stride of 2, because that divides our inputs into these non-overlapping 2 by 2 tiles. Then within each of those non-overlapping 2 by 2 tiles, we'll take the max entry. In this case, it's a 6, 8, 3, 4. So then you take the max entry inside each of those, and then that gives us our spatial compression. And you can imagine a whole set of hyperparameters here. You could say, what is the kernel size? You could change the kernel size. You can change the stride. You can also change the function that we use for downsampling. Max pooling is pretty common. You'll also see average. You'll also see anti-aliased downpooling sometimes. So these are all just ways that you can downsample these feature maps one at a time. Good question. We make a use of padding. Typically, you do not use padding inside of pooling layers. There's nothing mathematically preventing you from doing so. But in the case of max pooling, it would be kind of silly. It's basically equivalent to a ReLU. So whenever you're using max pooling, if you're also using a ReLU, that would be redundant. So typically we don't use padding in pooling layers. I'm actually not sure if PyTorch has a flag for padding or not in pooling layers. Yeah, so the stride would be another one of these architectural hyperparameters, but usually you don't tune these things too much. Usually the intuition behind a pooling layer, like honestly the most common is I want to downsample everything by a factor of 2 is like by far the most common operation. So then the most common thing to do would be 2 by 2 stride 2. Sometimes you'll do like 4 by 4 stride 2, but basically the most common settings by far is I want to downsample everything by a factor of exactly 2. Oh, that's a very good question. Do images all have to be the same input size? In all the language that we're talking about so far, yes. You're going to run into big problems if your input images are not the same size. So then things that you'll typically do to fix that would be like, one, you either resize all your images to the exact same size before you batch them to feed to the network. Sometimes you'll also pad your images out with zeros or some other value to make them all the same size but now padded rather than warped. Or you need to basically run these layers independently for images of different aspect ratios. So that's another thing that you'll do sometimes in more sophisticated training setups, is that sometimes you'll do what's known as like aspect ratio bucketing. So then from your training data, you'll bucket them into different aspect ratios, and then each forward-backward pass of the network will be on a batch of images of the same resolution and aspect ratio, but then each iteration, you might grab images with different resolutions or aspect ratios. But that's something that you'll see in some of the more common, larger production systems. Yeah, so the question is, where do you put these? These are usually interspersed with the convolution layers. So a pretty common pattern for convnets is to intersperse the convolution and pooling. So, for example, you'll see like conv pool, conv pool, conv pool, fully connected is kind of a prototypical convolutional network. Yes, that's an excellent question. Does this introduce non-linearity? So it depends on the type of pooling operation that you're using. So if you're doing max pooling, that's a nonlinearity. So in some networks, if you have a max pooling, you may not use a ReLU around that convolution because a max pooling is a nonlinearity itself. If it's an average pooling, that's also a linear operator. So then if you do average pooling, it's linear, so then you probably still would want a ReLU there. Okay, so then here's my quick one-slide summary of pooling. It's basically the same hyperparameters as convolution, except you've got this extra pooling function, which is what is the mechanism you're using to do the downsampling. Then the last thing I wanted to mention is this notion of translation equivariance. What the hell is that? So I said at the beginning of the lecture that we wanted operators that are respecting the spatial structure of our images, right? And that we had this notion that flattening our images into big vectors is somehow not respecting the spatial structure of our images. So there's a really interesting property that is shared by both convolution and pooling, which is one way to formalize this notion of them respecting the 2D spatial structure of the images. And that's this notion of translation equivariance. So it sounds pretty crazy, but the idea is we can imagine two different operators, two different branches. Along one branch, we can imagine taking our image, doing a convolution or pooling operator to get an updated image, and then translating the result by shifting that feature map to the side, for example. Then you could imagine changing the order of these two things instead. What we could have done instead is first translate the image and then do our convolution or pool operator on top of the translated image. And it just so happens that in this case, the order doesn't matter. If you translate and then convolution, you get the same result as if you had done convolution and then translate. Subject to some boundary conditions, blah, 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 blah. But like in sort of the limit of infinitely large images and blah, 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 ignoring some of these technical conditions, it's really interesting that you can actually swap the order of translation in space versus performing these downsampling or convolution operators. And that bakes in an important intuition about images, which is that when we're processing images, the features that we extract from an image should only depend on the content of the image and should not depend on where in the image where the absolute location in the image that content came from. So that means that, if I'm looking this way, it looks like people and benches. If I'm looking this way, it looks like people and benches. And the fact that it's over here on my right and the fact that it's over here on my left, I want to process that data in the exact same way. And that's an important intuition, an important structure that we want of images and of the kind of 2D data that we're processing. And this notion of translation equivariance basically is a way to mathematically describe how that structure is baked into these operators. So this is kind of interesting that it's a way that we can build in our intuition about how images ought to be processed through the design of our operators, not through the design of our feature extraction methods as we saw at the beginning. The question is, why do you do a translation? You don't. This is not something you're actually going to do. This is basically a mathematical curiosity, right? To be clear, that you should not generally do this inside of your neural networks. This is basically it's interesting to note that this happens to be true, but you would not do this inside of your neural networks. And if you're a mathematician, you call this a commutative diagram, and mathematicians love those things. Okay, so that's basically the summary of today. We talked about convolutional networks. We talked about, why they're interesting. We talked about these two new operators of convolution and pooling. And then next lecture, we'll see how to stitch those together into CNN architectures. And see you next time for that.